Hi everyone. This is Soumya here, and that's my colleague Shivang. We're both here to take you through our journey of how we decided to migrate our data from MongoDB to YugabyteDB. So we decided around 2 years ago to actually choose YugabyteDB as our primary data source. Um, why and all of that, I think, is a separate thing altogether. But while taking that decision, we that was like most of our data was stored in MongoDB, and we had to migrate that to Yugabyte. So we had to come up with a strategy that would work for all of the collections and all of the data that we have. So this is like basically the journey through the multiple changes that our strategy went through, the initial strategy that we thought about, and finally the final one that we tweaked around with. Before we begin with this journey that we're going to go through, I'm just going to give you a small context about what Yugabyte version we've been using for majority of this migration, which is 2.14.3. The hardware specification of our nodes being 8 GB RAM and 2 vCPUs initially to begin with. We changed that going forward. And the traffic in which we had to migrate was somewhere around 200 kbps with around something around like 2 TB of data. And we had to do all of this migration in live traffic. We had to migrate with minimum downtime if we could, right? Or zero time downtime if we could. That would be the best. So we looked back and we were like, oh, let's check out all the migration strategies that are out there that people are using. And we found that there are three generic migration strategies in theory. One being the Big Bang database migration, then the trickle database migration, and then the zero downtime database migration. The third one, I think we've kind of talked about that we want to use it. So you'll see glances of it throughout our journey. The first one, which is I'll just give you a small, in case you haven't heard about these, so I'll give you a small overview of what these three strategies are. Big Bang, as the name says, you just take the whole data on its own and then migrate it to the new database. And like in a blink of a, just like Thanos's switch, you just switch your traffic in a blink of an eye, right? The trickle database is something where just like the names themselves are quite informative. So just like the name suggests, like a water droplet trickles down um you know uh, anything essentially, or a table or a chair or something, right? Just in that, so in that way, you migrate a chunk of your data and then do the switching for that. And similarly, you keep doing that for every chunk of the data that you decide. Okay. And then the last one, as I mentioned, it's zero downtime database strategy, which is basically migration strategy, which is basically not taking a downtime at all while your migration is happening. So essentially something like having two clusters or similar things going. So we have incorporated parts of these in our migration strategy. That's why I've mentioned them. Like initially, for example, we started with a Big Bang, and then you'll see later on we used parts of trickle, and zero downtime, of course, had to be there. Now coming on to the frameworks that we actually used for migration from the application's point of view. Right. So the framework that we used was something called as dual read-write framework. I think it's being used by a bunch of migrations out there. But to give you an overview, what dual read-write framework actually means is that your application, so initially your application is just writing to that one database, right? Mongo. So by dual read and write, you're saying that since you're introducing a new database, so the same data you would write to both of these databases, and then you would read from both of these databases. Why are we doing so? Write, of course, makes sense because you have to migrate at some point. Why are we doing reads is because, like, why anyone generally goes for a just not a dual write framework and for a dual read write framework would be because you want to compare, especially because you're taking the data from one sort of database, that is a NoSQL database, to an SQL database. You need to compare the results that you're getting, see if there are any mismatches, if your queries work fine or not, especially if you don't want any downtime later on, right? Now the control that you want between the two databases, which should be a primary, which should be a secondary, and things like that, that you could use a control flag for that. We stored that control flag in Redis, but you could choose any database that you want. Using that, you could also control like how much part of your data, like which customer you want to migrate at what point of time. So we had done that specifically. And also whether you want your writes or reads to be primary or secondary, right? Using the control flag to do all of that. You could create the control flag in such a way. Now we talk about this framework, but how exactly do you do the migration? Like you can, we'll go through the phases of the migration one by one. So this is the generic framework that we had to begin with. So the dual read-write framework is already out there. This is the phases that we started with when we did our migration the first time. So our application was initially like the step 0, which was before we ever started migration, was your application was writing to Mongo. Then your phase 2 came in where you started, your reads and writes were already happening in Mongo in synchronous way, right? Which was right now your primary data store. Then you got in Yugabyte where you started writing your writes. All your writes were now going also to Yugabyte in a synchronous or asynchronous way, according to whatever you choose. We started with asynchronous, right? Because we didn't want our application services time to get impacted. Then eventually you move on to, like, now that you've started your time writes at a time, let's say T0, and everything looks fine to you, right? So then you start backfilling your data into Yugabyte along with your, so your reads and writes are still going to Mongo, your writes are going to Mongo, and then you start backfilling your data from whenever your data, like the last dated value of your data till the time T0, okay? So you backfill all of your data inside your Yugabyte cluster. And then, like, once you've noted all of these things, like you've backfilled the data and everything, again, you have to make sure that everything looks fine. You start your reads to Yugabyte also, again, in an asynchronous way at this point. Like we had done asynchronous way, you can choose it to be synchronous, right? So you do your reads and writes are going to Mongo, and your reads and writes are also going to Yugabyte. Now, when I'm saying your Mongo is primary database, the important thing about it being the primary database is that your UX or your client is being served the traffic from this data store and not from whatever is happening in Yugabyte. Okay. Why this is essential, we'll just see in the next stage, right? So once your reads and writes are going to both the data stores, your writes are being compared between Mongo, your primary and your secondary data store, and you find whatever you need to tweak around between in case you see any mismatches, right? The next phase that we come on to is where, so as you see in the third phase, right? You see MongoDB is your primary DB and your YugabyteDB is a secondary DB. Now, in this phase, suddenly we've switched Yugabyte to be the primary DB and Mongo to be a secondary DB. Your reads and writes are still going to both, but the primary and the secondary now changes. So that means your client and your UX is now getting all of the reads and writes via Yugabyte and not Mongo. So Mongo might be going in async or sync, doesn't matter, but it's not serving your traffic as such, live traffic, right? So this switch you make and you observe that for the time period that you want, because anything can go wrong, right? So you observe that for a little while. You just don't stop writing to Mongo altogether in a blink. You just maintain this state for some time, let's say for a day, for a week, whatever is comfortable with you. And then finally, in the last stage, you actually remove Mongo altogether. And now Yugabyte is your only data store at this point. Your reads and writes are going there. So this was the whole phases that we went forward with. Now we did this in production and we migrated a couple of collections because we were doing it collection wise. Each collection in Mongo was being migrated one by one. And then we observed that, there were some problems with the production cluster. So we started seeing some spikes in the load, like at different times, we would see like the load average would go suddenly too high. Now, as we mentioned here, it was like the original reason came out to be some bad queries, like bad sharding or queries, But initially, when the load average was going that high, our cluster would just go into a really bad spiral, and then it would be very difficult to recover from it. So we thought that let's set up a staging cluster and debug all of these things out for ourselves, right? So we set up a staging cluster basically, essentially to reproduce this crash of our Yugabyte cluster, to have a pre-prod environment where we could deploy anything before we go to production, and it would also provide us a safe playground for experimentations and POCs. Now, to actually emulate what was happening, to reproduce this crash, right, we had to emulate what was happening on our staging cluster. To emulate that, this is the kind of setup that we had done, saying that our application was now, along with sending it to Mongo, whatever your reads and writes are, it was also sending it to Kafka, where we had set up some consumers which are consuming from there and then spawning parallel threads and writing to the Yugabyte staging cluster. Now, these parallel threads, right, the number of parallel threads that each consumer would spawn was something that we could control, so that we could actually decide what throughput, with less number of consumers, we could actually create the throughput that was going on in production. So essentially, like we did something around like 2x of traffic. Luckily, we were able to reproduce whatever the crash that was happening in production. Actually, we were able to do much better than that, which is like take the load average to somewhere like around 100 or something. Um, and what we observed from that was there were a large number of PostgreSQL connections that were being made. Along with that, because the load average was going high, the reason that our cluster kept going in a bad state was because our OM killer was actually preferring to kill the tablet servers. So we adjusted the OM score because of that, and we looked into the load average case. Right. So before that, we thought let's confirm our hypothesis by going back to the timeline when this happened in production for us, and check out the number of PostgreSQL connection our production cluster was making at that time, which was something around 700, as you can see. Now the question came to us that how should we actually tame these connections, that like the huge number of connections that were being made. So here we have Shivang who take you through that journey and then all the rest of the modifications that we made the migration strategy.
Hello everyone. Now I will talk about how we solved our problem of unbounded database connections. We solved this problem by introducing a server-side connection pooler for efficiently managing the database resources. Earlier, we were facing problems with a large number of database connections taking up a lot of memory because each connection takes up a finite amount of memory. And Postgres and as well as Yugabyte, the version that we were using for Yugabyte does not currently support the manage for this database connection internally, right? So that management we had to do it by ourselves. So to do that, we do this by maintaining a pool of open and bounded database connections on the server side, which kind of serves as a purpose of multiplexing large number of clients to a much smaller actual number of connections. Additionally, from performance perspective, it also reduces the cost of opening and closing connections again and again. So now we are using Odyssey by Yandex in our production, which is a scalable SQL pooler. So we had an option to choose from poolers like PG Pool, PG Bouncer, or PG and Odyssey. But we went ahead with Odyssey because of the support it provides, right? It provides supports for SQL databases like Postgres. So as you can see from the diagram, in our production, each Odyssey process is kind of co-located with the Yugabyte server processes, right? So now, since the connections are now bounded on each server, application scale-outs does not increase the number of the connections. On the other hand, if we want to, increase the number of connections, we can easily do that by adding more Yugabyte nodes. Additionally, Odyssey, which we are using, is based on PG Bouncer, which just maintains connection and it does not do any load balancing. For the load balancing part of these connections, we are using HA proxy, which connects to the clients to ODC. So now that we have solved our previous stability issues, we restarted our migration, but this time introducing a new component called as a Yugabyte staging cluster. Like before, our application now reads and writes to Mongo, but now it also writes to Kafka in parallel, which is then consumed by a Kafka consumer, which in turn writes to Yugabyte staging cluster. And the next step, of course, is to we write Yugabyte in sync. So it is like dual writes now instead of just dual writes. Now, after turning on dual writes with staging cluster in place and backfilling the data from Mongo to Yugabyte, it was time to verify the data we had migrated. After verification, we saw that there were some inconsistent data or mismatches in the state of the data between both the databases. So these mismatches were actually we could categorize into three types: mismatches due to race conditions, mismatches due to difference in data model in both the databases, and ignorable mismatches. The first type of mismatches was because of the race condition which arose due to async nature of writing. And after finding this out, we changed our strategy to write to both the databases in sync instead of async. Since we are migrating from a NoSQL database to a SQL database, second type of mismatches arose due to difference in schema in both the databases. And the third type of mismatches arose due to race condition when comparing the records from both the databases, which were basically ignorable. Due to this inconsistent data, we found that we were, stuck in the, migration loop where we had to repeatedly stop the migration process, fix the migration code, test the fixes, and then restart the migration process from the beginning. To solve this issue, we came up with a new strategy of trickle-down migration, which were actually based on some achievable milestones. Now, instead of directly jumping to production, we did the staging migration first, which covered the milestone of zero mismatches in writes code path by using some test domains which already covered like 80% of the code paths. After completing the staging migration, we started migration in production, achieving the milestone of zero mismatches in read paths. So, in nutshell, the strategy is based on performing rapid multiple iterative sampling instead of fixing a large volume of data at once. So this was the final strategy that we implemented for our database migration. So now you may be wondering, like, when should we use dual writes for our migration, right? So dual read writes can be chosen based on any of these factors. Firstly, if there are less chances of data inconsistencies. So this was true in our case because there were less frequent updates. Secondly, if your data model is quite simple and it does not have any foreign key relation with other entities or other tables, right? And lastly, if there is less schema changes during the time of your database migration. So these were some of the alternate strategies that people can use, like using CDC or taking a dedicated downtime. But this entirely depends on the individual use case. I won't get into much details about these strategies, but maybe this is a topic for a separate talk. Thank you so much for listening. Have a nice day.